Welcome back. We were talking about nonlinear devices and nonlinearity, how it affects, and in that discussion in the last period we have seen it generates intermodulation products, and we were trying to understand the intermodulation product and some manufacturers how they define the intermodulation product in terms of C by third order intermodulation product, C by 3 IM. But that intermodulation product C by 3 IM is only for 2 carriers they define. Now, what happens when it is multiple carrier? What is the term they use? They use a term called noise power ratio. This is for multiple carriers, that is greater than 2, and this NPR is defined as noise power density. That noise power which is generated due to multiple carriers is going to fall at one place. So, that is called desired bandwidth. So, it is noise power density outside desired bandwidth divided by noise power density within desired bandwidth. It is very simple. Let us say over this band operation is going on, many carriers are placed, and a particular area, in this area we want to see what is the effect of other carriers falling into this. Here is my interest. So, here is my actual operating carrier, on that how much noise is falling over this. So, noise power density outside this and noise power density which is falling into this, that will fall. Initially there is a noise power density and it will increase because of this intermodulation. So, it is a measure, people do measurement using notch filter and noise generator, but I just wanted to tell you that there is another term which is NPR. So, we have come across 2 terms, C by 3 IM and NPR, noise power ratio. This is defined for 2 carrier operation or characteristics of the nonlinear device with 2 carrier operation. This defines the characteristics of the device or system with more than 2 carriers, multiple carrier operation. That is only the. Now, the meaning is that if NPR is higher, then linearity is better or linearity is poor. It is linearity is better, because when this is higher, this noise power density within the desired band is low, then only this becomes higher. So, noise power density within the desired band becomes low when the intermodulation of others are not falling here. That means system is operating in most of them are in linear region. Nonlinearity can generate the intermod. So, there is no nonlinearity or less nonlinearity. So, it is much better, linearity is much better. This much is enough for the definition. There is one more thing that people come across, that is called passive intermod product. This is not by active device. When there is a metal to metal contact, like in connector, cable, input to the antenna, etc. Due to corrosion, oxidation, contamination, that RF intermod is generated. Because of these things, it creates a nonlinearity in the metal or the conductor which is carrying the RF. So, since there is a nonlinearity, that intermod is generated. This is called passive intermodulation product. So, in case of high power antenna, this with higher power, that also affects, but this cannot be modeled so easily since it is a random phenomena, but this can be this has to be taken into account during the system design. So, we will go into further into this nonlinearity. Let us look a little more further into it. What is the other effect? We have seen Pi versus P out, that is in dBm or dBw, normally it is in dBm, and we have seen this goes as a linear curve and then it saturates, and there is a definition of a 1 dB compression point and a third order intermod which gets generated, and that also saturates, and its extension goes to a point which we call intercept point IP, and this is 1 dB compression point. In terms of input and output, it can be defined. Now, there is a noise below this. So, actual operation for linear range of operation, we can do just, we can assume 1 dB is very small compared to the total range on which we can operate. So, this one in terms of output, this is our linear dynamic range. This is the linear fundamental power curve P omega 1. So, this is the linear dynamic range. So, this is P 1 dB minus this is the noise floor, which is noise power. So, LDR linear dynamic range in dB is 1 dB, that is output 1 dB compression point minus noise power. So, that is the linear dynamic range, but though it is linear dynamic range, our spurious starts coming in. This is the third order intermod product. This is the third order intermod product P 2 omega 1 minus omega 2 or P 2 omega 2 minus omega 1, one of them we take. Now, this starts growing above the noise level at this point. So, therefore, we can see that below this point, that the spurious noise, which is supposed to be the third order intermod, that has not come. Spurious noise started coming from here. As we go more input, spurious noise starts coming here. So, this dynamic range, this one, we can call spurious free dynamic range. I can color it. This one is spurious free dynamic range, where the spurious is started coming in just that point to the linear dynamic range point, and this is the linear dynamic range from the output point of view. Same thing can be said in terms of input, but since we are talking about the amplifier, it is the output spurious free dynamic range. So, spurious free dynamic range is P omega 1 by 2 by P 2 omega 1 minus omega 2 at 2 omega 1 minus omega 2 when it becomes N0. So, from N0, this is given in ratio, it can be put into dB also. Let us try to calculate how in terms of our intercept point, because that is the specification. So, SFDR is equal to p omega 1 by p 2 omega 1 minus omega 2, and p 2 omega 1 minus omega 2 we have seen it is p omega 1 cube by OIP3 square, output intercept point square. So, therefore, I can write p omega 1 is equal to OIP3 square into p 2 omega 1 minus omega 2 and to the power 1/3, because this was cube, sorry, 1/3 because this was cube. So, p omega 1, now this p omega 1 we can substitute here. So, we can get SFDR is equal to OIP3 square multiplied by p 2 omega 1 minus omega 2 to the power 1/3 by p 2 omega 1 minus omega 2, p 2 omega 1 minus omega 2. So, p omega 1 I replaced here, and by readjusting this we can get it is equal to OIP3 by 2 by p 2 omega 1 minus omega 2 2/3. This is in ratio. So, in dB SFDR, in dB you can write 2/3 of OIP3 minus p 2 omega 1 minus omega 2. Now, this is the definition of the spurious free dynamic range in terms of OIP3, but you know, it is not only the dynamic range. At the lower side this is the noise, and so therefore, when this becomes the noise power, so it is 2/3 of OIP3 minus N0. But many of the devices and systems, they won't work until a particular SNR is achieved. After that minimum SNR, they will start functioning. So, the dynamic range should have been defined that with, when I consider the SNR, SFDR in dB will be 2/3 of OIP3 minus N0 minus signal to noise ratio. That is the minimum signal to noise ratio with which it should operate. So, with that, this can be expressed in this form. Now, let us do some quick calculation. One thing I missed. Let me explain that. Let me explain. This is very important. This curve, that is, we have linear dynamic range and we have spurious free dynamic range. We may consider the SNR, we may not, depending on the requirement. Now, really my spurious free operating point is this. This region started getting into spurious and nonlinearity. So, if we want to avoid the nonlinearity as well as the spurious, how much back off we should go. So, we have talked about the back off, that is input when it is getting into saturation 1 dB compression point. From there, if I reduce the input, it is called input back off. Similarly, from the 1 dB compression point, it will come down as a output back off. So, for spurious free operation, one is nonlinear operation. For spurious free operation, how much back off? This minus this. So, for spurious free operation, this OBO will be this much for spurious free operation. This is another interesting idea. So, let us take a quick example for a receiver. Let some data is given. Noise figure is 7 dB, 1 dB compression point is 25 dBm, and let us say it is output reference, and gain is 40 dB. That output intercept third order intercept point is 35 dBm. That receiver is receiving a input, and it has a antenna in front of it, so that temperature of from the antenna it is receiving 150 K. It has a bandwidth of 100 megahertz. Now, can we find that linear dynamic range, spurious free dynamic range? So, what we have to find out, that if you remember spurious free dynamic range and linear dynamic range, we have to find out what is the noise, because OP 1 dB output 1 dB compression point minus noise power. So, noise power has to be calculated. So, for noise power we have been given some information. Let us see what is noise power. If you recollect, it is G into K into the bandwidth, and then it is multiplied by F minus 1 in case of, we can say noise figure, noise factor minus 1, because F is given in noise figure is given in dB, we will convert into ratio, and multiplied by the temperature, normal temperature T0, which is 290. So, if you put these numbers, the gain is 40 dB, so it is 10 to the power 4. I am converting all dB into linear ratio, and then K value is 1.38 into 10 to the power minus 23, if you recollect. Then the bandwidth is 10 to the power 8, and then we have this multiplied by 150, that is antenna noise temperature, and that 7 dB noise figure you convert into ratio, it becomes 5 F minus 1, and this multiplied by 290. So, this multiplied by this, and when you calculate, it comes out to be 1.8 into 10 to the power minus 8 watt. It is minus 47.4 dBm. Do your own calculation. Don't copy my numbers what I have done. So, the LDR value will become P 1 dB compression point minus N0 in dB now is 25, which is given 25 dBm, and this is also in dBm. You have to remember to convert, if this is in dBm, this also has to be dBm. If this is in dBW, convert into dBW. So, both of them should be same. This minus 47.4, and that becomes 72.4 dB, and then the SFDR value is 2/3 of P3 minus N0, and that is you have the P3 supplied, that OIP3 is 35 dBm, N0 is already obtained, and 2/3 of that you get in dB 54.9 dB. Now, if I ask you, I mean this question, I extend that, find out that output back of spurious free condition. So, then as we have seen that it is LDR, that is output back of will be is equal to LDR minus SFDR, that is 72 minus 54.9, which is 17.1 dB. Now, this is just an example for you to work out. Similar example we will try to give in assignment. So, let us see that 3 effects we have seen, that is, we have seen that power in to power out in dB, the curve goes like this, linear and then non-linear. So, this one is termed as AM to AM conversion. Similarly, we have seen there is a gain compression. If there is a gain this side and power in this side, initially there is a constant gain, then gain will start falling when 1 dB compression point coming and beyond that. But this is on amplitude. There is one more effect that happens, that is in phase. So, input phase to output phase, if I take the difference and call it delta phi, that is phase. Input to output phase, that is delta phi, and if we input we increase, then it is constant and then the difference increases. Now, this is called AM to PM conversion. Now, these are the causes of nonlinearity. In briefly, that amplitude gets nonlinear, gain gets compressed, is called gain compression. AM to AM conversion and AM to PM conversion takes place. Now, because of that, there is the effects are, if I draw a spectrum, initially the spectrum may look like this. Due to our filtering, it will be like this. This is the spectrum. Now, due to intermodulation, the spurious gets generated, and the new spectrum, the spurious will be spread at different frequencies. So, new spectrum will be enhanced. So, this is enhanced and it spreads further, amplitude spreads further. So, if your operation area is this and the adjacent channel is coming, you are interfering. So, spectrum spreading generates that adjacent channel interference. This is the effect of spectrum spreading. This is one of the serious things that happens due to intermod. One is the intermodulation product generates the spurious within the channel, so that your signal to noise ratio or dynamic range reduces. Another is spread the spectrum so that it interferes in the adjacent channel. Adjacent channel interference increases. There is one more problem because of the phase nonlinearity. Let us see nowadays our operation in this recent days communication are mostly phase modulation, BPSK, QPSK, the phase shift keying modulation. Now, let us try to draw a constellation diagram of a QAM. This is IQ channel. Say 16 QAM constellation diagram is like this. These are nothing but the vector points. So, the decision boundary for at the receiver to identify where the vector is and decide that which bit it should be. Each of these vector points represent a particular symbol. So, in case of QAM, this will be 4-bit symbol. Let us say this is 0101, this is 0111, like that. Each of them represent a symbol which is a combination of a couple of bits. Now, if this is detected properly, this detection can takes place within a decision boundary. So, we can call that this decision boundary is in this square. Now, this vector may get into different type of noise. So, its vector location in amplitude as well as in phase it will be varying. So, in terms of phase, when it varies, it may move in this direction or in this direction. So, because of our nonlinearity, as we said that the phase may change, so this vector will change this direction and this direction. And similarly, there is a possibility that due to Gaussian noise, there will be the vector may be anywhere in this location. So, because of the phase nonlinearity, the system may change, the constellation may change, and your vector will go into the other decision level, and so that it will be wrong decision is taken. So, this is, let us say, decision boundary for this particular vector, a decision boundary. Now, if it changes more than the decision boundary, then it will be detected as a wrong symbol. This symbol, let us say it was 0101, and this symbol is 0110, and so this will be detected wrongly when it crosses this. Now, this is another effect of a little more explanation of the constellation and tilt due to introduction, and this increases the BER. Now, one quick thing is the mitigation is very simple. That is, if you have a nonlinearity like this, so you pre-distort the signal like this. So, effectively you get a linear region. This is pre-distortion, this is the actual, and this is the resultant. At the transmit side, it is done by pre-distortion of the signal, so that when it passes through actual nonlinear, you introduce a nonlinearity, passes through other way nonlinearity, you get a resultant linear. And in the receive side, it is done by equalization. This is very brief idea of the mitigation of the nonlinear system. So, till now what we have covered is the definition of some terms, and then we have, in the definition of terms, we have come across 1 dB compression point, third order intercept point, C by 3 IM, then NPR. Then we have tried to estimate their values individually in the device or subsystem and in a cascaded subsystem. Then we tried to show you what is the effect of nonlinearity in terms of gain compression and dynamic range reduction, and then we have very briefly touched how the mitigation is done, that is by linearizer or equalizer. So, with this we have covered briefly the nonlinearity aspect of the devices and subsystem we come across in the satellite communication. Thank you very much for this topic.